Hello and welcome to this new video where we are going to discuss mathematics or physics on the board. In this particular case, what we are going to do is basically continue some of the things we've looked at in exterior calculus and how it applies in traditional vector calculus. And in particular here, we are going to show how from exterior calculus we very easily obtain Stokes Theorem. Okay, so basically that's what we are going to do today. Okay, so in a previous video that maybe you want to look at, we've looked at deriving the divergence theorem from the fundamental theorem of calculus in exterior calculus. And so here we are going to do the same thing, but with Stokes theorem. So the thing is that, again, just as a summary of how these things work, just in case you didn't want to check the video from before, essentially we work in the case of exterior calculus in Rn, and exterior calculus in Rn, you define what you call an exterior product between two differentials, and it is defined in such a way that du wedge, so that's called a wedge product, wedge dv is equal to minus dv wedge du. Okay, now a consequence of that is that basically any differential form, if you take the exterior product, of any differential form with itself, is going to be zero. Okay, and that's something we are going to use afterwards. Now, the way I like to define exterior derivative is by defining how that works for a zero form, which is basically a scalar function from Rn to R, that I call here, for example, f, and by definition, df is returning simply the total differential. So nothing special here. However, for any other k form where k is less than or equal to n, then the general form usually forms, for some reason, are called omega. So they are going to follow this particular definition. So you see that you need to be careful. The indices have to be all less kind of than each other, at least in the formulation I've chosen here. The reason why is because they can't be equal to each other. So that's the first thing, because if they're equal, you get zero from that particular property. And the second thing is that if you were to take some values that are sometimes, less than, so for example, let's say I1 is sometimes less than I2, but not always, etc., then you've got the risk of double counting things. So you don't want to do that and have the right number, let's say, of vectors to expand upon. So essentially, this is going to read like that, and then you simply define d omega as being d of omega here. So omega is a component here. Omega I1 to Ik is a component. You can take it as a scalar function. And so here you evaluate d omega in the same way you would evaluate df here, and then simply wedge the rest of it. Okay, so that's really the best, at least in my opinion, the best way to remember this one. And then finally, there is a fundamental theorem of calculus. So if you take any subdomain of Rn, it doesn't need to be a three-dimensional domain. We are going to see that in a minute. And then we've got d omega, the boundary of omega, and omega is a k form where k is less than or equal to n. Then we can write that the integral of omega over the boundary d omega is equal to the integral over omega itself, so the domain, and then of d omega this time. And that's obviously working only under these particular circumstances. So omega and d omega have to exist everywhere in their respective domains of integration in that equation. If that's not the case, you can't use it. Okay? So that being said, our problem now is basically to look at n is equal to 3, and then we look at a form which is like this. So it's basically a one form, and this one form is omega x dx plus omega y dy plus omega z dz. So you can interpret this as being basically the differential element of a line integral, okay, of a circulation integral. And And basically that's it. So we've got a vector field omega, and then we look at the circulation of that vector field along a particular curve. Okay. So basically that's it. So now I interpret therefore d omega as being a curve, and that's a closed curve. And then, so basically curve bounding omega, and therefore omega is a surface. Now the surface need not be planar. It can be a complicated surface in 3D, but basically it is bounded by this boundary, closed boundary curve, closed curve. So bounding omega, which is inside R3. And that's the surface, right, omega. So that's kind of the idea. So now let's look at implementing the theorem. So we've got the integral of d omega, and then we have omega dot dl, and that's going to be the integral of the one form omega, and then I'm simply applying the fundamental theorem of exterior calculus. So I'm going to get d omega over omega itself, and then d omega, I apply what I know. So this is going to be the integral over omega, and then of d omega x wedge dx plus d omega y wedge dy, then plus d omega z wedge dz. So that's what I have. Now, I need to be a bit careful and write these things kind of slowly but surely, okay? So I'm going to write here d omega x is equal to d omega x dx dx plus d omega y, d omega x, sorry, dy dy, and then plus d omega x dz dz. And in principle, I've got to do the same for all the rest. So I've got d omega y is equal to d omega y dx dx plus d omega y dy dy plus d omega y dz dz. And finally, I've got d omega z is equal to d omega z dx dx plus d omega z dy dy plus d omega z dz dz. Okay? Now, what I'm going to notice here is that d omega x is wedged with dx. So I know that this component is not going to contribute because dx wedged dx is 0. Likewise, d omega y is wedged with dy, and I know that then dy wedged dy is to be 0. And basically what that means is that there are only two of these kind of terms that are going to contribute to the inside of the integrand here. Okay, so that's what I'm going to directly put together. And yes, that's exactly what I'm going to do. So the way I'm going to do is I'm going to directly split things. So I'm going to multiply it with this term, and then yes, and then basically expand, distribute the product because it's distributive, right? So it's going to be quite. How to write this? So let's start here. That's a DL here. And that's going to be equal. So now I need to evaluate that part. So that's omega. And so let's have a look. So we've got d omega x and then dy wedge dx plus d omega plus d omega x dz dz wedge dx. So that's coming simply from d omega x wedge dx. So that's what this term is. Okay, and then we continue. So plus d omega y dx wedge dy, and then plus d omega y dz wedge dy. Sorry, I'm writing a bit smaller, and then plus d omega z dx wedge dz, and then plus d omega z dy wedge dz. Okay, so that's what I'm getting from simply distributing the product and also accounting for dx wedge dx is 0, dy wedge dy is 0, and dz wedge dz is 0. Okay, now what I'm going to do is group the terms by realizing that dy wedge dx is the same as minus dx wedge dy, and so I can factorize these things, and that's what I'm going to do here. So I'm going to get the integral over omega. So let's see, we have a dx dy here, so that's d omega y dx. Okay, and then I'm going to get a minus coming from here. So minus d omega x dy, and that's dx dy. Okay, and then I continue. So then I'm going to get plus, and then plus I get, let's say here, dz dx. So I've got, yes, so I've got, yes, so I've got d omega x dz minus d omega z dx, and then here that's dz wedge dx, and then we get plus, and the final one is dy dz, so plus d omega z dy minus d omega y dz, and that's dz dy wedge dz. Okay, now as it turns out, this corresponds to essentially what we call the curl. And in fact, here, if I introduce basically, so this is going to correspond to the integral of the curl of omega, okay, and then dot product with ds. And here ds is something I talked about, but here this time I can write it specifically. That's going to be dx dy, let's say ez, and then plus yes, let's look at it this way, and then plus dz dx ey, and then plus dy dz ex. Okay, so that's the basically that, you know, ds here is kind of a vector, but of course it has to contain components of a parallelogram, and so that's why I'm still using the wedge products here. So it's a bit of mixtures of notation here, but that's kind of the idea. Okay, that's kind of how this is supposed to work. And so here you see that if you equate this to that, you get what is called the Stokes theorem. So the line integral of a closed curve of a field omega, of a vector field omega, is equal to the flux of the curl of that field over the domain that particular curve is bounding. Okay, which is a surface in 3D, and basically that's it. So of course this is something very important in electrodynamics and in fluid dynamics as well. So basically that's the Stokes theorem. So again, provided you're working with rectangular coordinates, then this is a very, very general result. Okay, it's going to work in all possible cases. I don't need to draw any specific thing. So I know that some people can kind of prove it by calculating the flux and somehow taking some differentials and so on. Yes, okay, that's fine. But here I'm just basically applying a very, very general result that works, in any dimension for any kind of forms, etc. And then simply showing that one special case of that is the Stokes theorem. Okay, so that's the idea, and basically that's it. So again, we are going to see in some later videos, probably not next week, but some others, basically some application of that in fluid dynamics, for example. Okay, so if you've got any questions or comments, by all means, do let me know in the comment section, and otherwise, see you in the next video.